days. It was like one of those heating years in the Arctic.
Hello.
And then it was gone.
Thanks for joining us today. I'm delighted to welcome our next speaker to the stage for the Conversation with Science, which is a series of conversations we're having every day of the programming here at the Climate Hub to bring science into the programming. So delighted to welcome Giles Whittle, the World Affairs Editor of Tortoise, to the stage with his speaker Anne Youngblood, Principal Researcher at the Natural History Museum. Thank you.
Thank you. We're sitting at the right end of the sofas, I think we are. My goodness, the lights are bright.
Yeah.
So when it comes in about 20 minutes to seeing if any of you have got any questions, I'll have to do this. Thank you very much. Yes, my name's Giles Whittle. I'm an editor at Tortoise. And I was saying to Anne before we came on that I feel very lucky as a journalist being able to ask questions in settings like these and others. But I also envy you, because Anne has been to the high Arctic and the Antarctic more times than I've been to Glasgow, and that's a lot of times because I have a son at university here. So I envy you that enormously, and I hope that in the short time we have available, we can talk a little bit about how you do the science there, the sort of logistical challenges. But first of all, let's get to the nuts and bolts of it. Because, and I'm going to leave you to say this, but I'm just going to try and introduce you to, and you can say if I've understood the basics. By studying tiny, tiny organisms in the poles, you have learned, at the poles, you have learned stuff about the habitability of those areas and what will happen if they change that we didn't know 20 years ago because we didn't have the tech to find out. Can you explain a bit more about that, and please correct me where I've got it wrong?
I'm really glad being here and able to talk about some of the work we're doing at the Natural History Museum. So we study microscopic life in the extreme environments, and microbes are really important in the extreme environments because it's so extreme that not much higher organisms can really live on the ice shelves and on the glaciers. And so we go to these environments and we want to know what's there, because until quite recently, people saw there these sterile environments. There's just ice, and nothing is living there. And now, with the tools, so with the advent of DNA sequencing technology, because we can't see these organisms with our bare eyes, naked eyes, so we had to have the sequencing technology. We can go there and we can see what organisms are doing there, what's their ecology, how do they contribute to carbon cycling and oxygen production, and then also maybe how they're going to interact with some of the glaciers, and so we understand what's the biodiversity, where can they live, and how what's there can change all these global cycles.
And are we talking now specifically about the Antarctic or both?
It really applies on any extreme environment,
right.
The Arctic and the Antarctic, especially the environments like the Canadian high Arctic, where there are still the ice shelves, or we go to the McMurdo Drivers where the desert. So really, the Arctic and the Antarctic. We have, on the one hand, the poles are apart, but there are similar systems there.
And initially, when I read a little bit about this is called the microbiome, right? The focus of your research. I thought that you had found ways, basically, to track climate change over time in a sort of comparable way to ice cores. But the point you were making just before we came on stage was a subtler one about the sort of dependence of these algae, really, on a very, very specific environment and the risk to them if that changes. Can you explain a bit more about that?
Yeah, so microbes, I guess they're very versatile. They can adapt to lots of conditions, but they're kind of adapted to the diverse condition of an extreme environment, like living in a meltwater pond on the ice shelf. And so being on this ice shelf, they're probably quite sort of happy living there, but they rely on the ecosystem. So if we lose habitats like the ice shelves, we're probably going to lose all the biodiversity in there, all the knowledge in there. These organisms they have to live to these really extreme conditions, and so they often have these ways to cope with it. And so there's a lot of potential to find new, like for biotechnological application, or potentially find new medical drugs in these things. So everything relies on I guess, the existence of these ice-based systems that are sensitive to warming.
You went to the McMurdo Ice Shelf in particular, and a particular place there. Tell us why.
Yeah, well, there's the Antarctica, there's the McMurdo Ice Shelf, and it has these areas. It's called actually the dirty ice, the area, and there you have these meltwater ponds. And so we went there and thought it was very striking. But already the explorers, like Scott and Shackleton, they went there, and when they did their exploration to find what species, and they went there and they collected samples. And so
this was when, and what exactly did they bring back?
Like 1902, 1903. So
okay.
being at the museum, so at the Natural History Museum, we have this vast collection, including some of the specimens that were collected during this expedition. They are sitting in our cupboards, a specimen, and they've been sitting there since that time. And then when we study the biodiversity, we've been thinking about, okay, we know what's there, maybe what conditions will make them change, but we then were thinking, okay, what is the time scale of that change? What would happen in 100 years, like kind of before the ozone hole and human activity, because we actually have a time point for the polar regions, or Antarctica, when people were there. And so it was right at the beginning of when they were there. And so we went to the McMurdo Ice Shelf, to the same site as the expedition teams went, to compare the samples and to see, can we track changes of this algae biodiversity across 100 years.
And what did you find?
And so we found that first we can use the sample because they were stored in cupboards for 100 years. We can use them.
That's the amazing thing.
Yeah.
You were able to, is it sequence the genome of these stored samples, even though they had not been frozen, they'd just been left in a cupboard?
Yeah, and so we started looking at genes to identify the species in there. Yeah, so we've been able to use these DNA techniques to get genetic information of these samples. Yeah, and that's really amazing that we now know that we can use these samples to study biodiversity and address questions like climate change.
And I sort of interrupted you, but when you made the comparison between early 20th century and early 21st century, what had changed? And
so we've found actually very little change. So it's kind of very good news. So we found that the communities were very, very similar. And so we think they are these communities that are highly adapted living in this environment and dealing with maybe the extremes of that environment, like being frozen, having 24-hour sunlight, having lots of UV light. So they seem to be able to be resilient to this environment, but they are likely very specific to the environment. So if the habitat would change, if the ice shelves would be lost, we're probably going to lose that biodiversity.
And does the lack of change across that 100-year time span correlate with what we know from other sorts of research about their habitat? I mean, for example, sort of melting and sea surface temperatures, have they all stayed remarkably stable in that part of the world over that century?
I think we probably, there can be seasonal fluctuation, and there have been, studies, I would say not everything stays the same, and it really depends on the habitats. And so I think there is still actually very little data where people did time series of ocean algae, like the phytoplankton, which is basically a microbiome. Like all this food web is driven by the ocean food web's biomicrobiome, and it's only now with the sequencing technology that we can look at these questions. So in the future, people will get more like ice core, like sediment cores, and we're going to people will more and more try to get the DNA out of that one. So then we can go back not just 100 years, but hundreds and thousands of years. And all this is sort of possible now with the DNA technologies.
Right. So that's in a sense a glimpse of the past. I just want to be clear about one thing. These algae, are they sitting on top of the ice? You're able to study them without getting in a dry suit and getting underwater?
Yeah, so these algae, they live on top on the ice. So basically, as in the polar regions, as soon as you get water, you get life. And actually, there's a surprising amount of water, like liquid water, in the polar regions. So you find it as on the ice shelf, you get meltwater ponds. There are ice-covered lakes, but they still have, they have permanently water in them, and you get life in there, and you get life on the glaciers. So they're sitting on top and forming these actually quite complex microbial communities that are quite productive systems. So people did calculations. For example, they looked at the Hunt Ice Shelf, which is a northern Ellesmere Island, and when you go there, it looks probably like just slime and mud, but people looked at how much biological life is there, and it actually is in comparison to probably hundreds of polar bears, because everybody thinks about life of the polar regions, thinks about penguins and polar bears, but they are mainly at, I guess, the edges of the system, but there is a lot more life there, and that's all microbial.
And we're going to come to some questions, if there are any, from the floor in a minute, because I can see the timer ticking down. But I just want to be clear, from your research, you regard these algae as, are they in any sense indicators of where climate change might take their habitat next? Or are they rather, is it better to think of them as you were saying, examples of their own dependency on a very specific set of conditions, and so it's more a case of showing the biodiversity loss risk from climate change that we're aware of from other sources. Is that right?
So we definitely think that these environments are centennials of climate change, because they're all dependent on the ice and the conditions, and if there's warming, they will change and lose. But there is now this ongoing research, so it's part of our research actually to find microbial properties to see if there are indicators of change.
Right.
So it's actually a big question in polar sciences now to see what does it change, and can we track it, and how can we track it?
Do we already know the potential knock-on effects if we lose these algae on the food chain, for example?
For say the oceans, they are driving the food webs of the oceans, and if there would be a change in the algae in the ocean, it could have an effect on the food webs. So there have been studies by colleagues in Canada where they looked at the effect of fresh water coming off the Greenland ice sheet, and so suddenly there is more fresh water in the ocean, and they found that it led to a shift in some of the algae in the water, and then if the algae are different species, there might be a different food source, and so that could actually have a big effect on the whole system and even like the fisheries.
Okay. There's definitely something that I still want to ask, but is there anyone who wants to ask Anne about, yes, at the back under the light. Can we get a microphone?
Hi, thanks very much. Stephen Wallace from the University of Edinburgh. Your research sounds fascinating. You spoke quite a lot about how your research can be used to track the effects of climate change over time. But you mentioned briefly that your research also could potentially enable the identification of new biotechnologies that we can use now to, I guess, mitigate the effects of climate change today. Could you maybe go into that in a bit more detail, maybe what you found when sequencing these microbes?
Sorry, what was the cryotechnology? Sorry, what?
Biotechnology.
I think I was more about, so I think some of the effects, so I think people see that there's a lot of source for maybe biotechnological application, like more sort of pharmaceuticals or biotech in these areas.
Have you found anything?
So there are some products sort of used in science. There is like an enzyme that's now quite commonly used in biotechnology that was isolated from an organism from the Arctic. But then there is the important thing, washing powder. So there's the thing about cold enzymes. So if people want to do their washing at not warm temperature, they need enzymes that are working at lower temperature. And so these enzymes that function at lower temperature is something that could be obtained from these organisms adapted to grow in colder water or colder systems.
Great, thank you.
Were you wondering, sir, about potential applications for direct climate change mitigation? You know, the sort of possible use of algae that we hear of as a carbon sink?
Yeah, exactly.
Is that anything? Is there any read across there?
Well, I mean, there is. I mean, algae are. I mean, there is a carbon sink through the marine systems, but I guess there is a big discussion to foster, like kind of to do, and I think it's quite contested whether to actively promote to create blooms, like putting nutrients in the water and then seeing increased production. I think there is. I think it's quite complex topic, and I think there is a big science concern by doing it and manipulating the system.
Certainly, it's controversial as to whether you introduce, whether you mess with the system.
So
but are you able to measure the sort of absorptive capacity of the microbiome that you're working with, the carbon absorptive capacity?
I mean, there are probably, so our work hasn't looked, say, on the ice shelves, because what the carbon sort of sinks or how much carbon is bound with it, but surely there's a lot of research going on marine sciences that look at this and modeling these systems,
Thank you. Anyone else? Yes.
Thanks, hi. I missed, sadly, the beginning of your talk, but I was drawn to this conversation because I'm aware that there needs to be a lot more conversations to be had between laypersons like me and scientists. And I wondered if you could share your observations of COP26, navigating this space, this debate as a scientist, and whether you feel that the space for your voice and work is broadening.
So it's like my first day at Cobb, but overall from Natural History Museum, we are quite a big group here and involved in various activities, and I feel there's a lot of discussion going on and a lot of interaction between science and policy and the public.
We've got a couple of minutes left, and I just want, you've had 15 expeditions to the poles. Describe the physical obstacles and perhaps, if it's also relevant, the exhilaration of working in extreme conditions like that. Have you ever found yourself in a tent, in a blizzard, on an ice shelf, wondering if you'd ever get home in one piece?
So not quite, but we had quite, so I think it's an incredible area, like landscape to work in, and I think everybody going there really appreciates it, and everybody who goes there, everybody I talk to, people who've been there, going there for their whole career, they still think it's we're very fortunate to able to go there and be in this space, and it's just very, inspiring landscape to work in, I mean, we had quite tough conditions, so we usually go out and then we camp, and it's can be quite cold. I mean, we get these amazing kits, like clothing from the programs, but it can get quite cold, so like in the morning you wake up and your water bottle is frozen, and we had quite bad weather, so we have like our tents, and then normally you just put like, I don't know, a little pack in the soil, but we kind of have these massive, if you go to the outdoor store, and you have the really big ones. So we use them, and we put them into the ice, and then rocks on top, and every evening we have to make sure that all the straps, everything is really tight, that the tents are not flying away. And one thing we had where I think we were quite fine, but we sort of nearly once ran out of food, because we were in a camp and we were fine, but then there was the weather from the station was really bad, and they were supposed to come in helicopter and resupply us with food, and so they couldn't come, and so we were sort of fine, probably said, we'll be fine another few days, and otherwise we might to go to the ration, the dehydrated food. But then they came and it was all good and we had lots of food.
Well, I should imagine that in the future you'll be resupplied by zero-emission drone rather than
that's
helicopter. True. Thank you. I think it's a really interesting question about whether this process can expand. I mean, clearly at the Natural History Museum you already have a platform, but it's interesting to see the sheer variety of voices. Anyway.
Actually, I can say about the communication. So the museum is involved in a really cool activity in space here in upstairs in the nature bar. So there is like the whole day, every day, they are like a mix of explorers, museum scientists, artists. They're up in the nature bar and giving presentation, and it's very small, and so everybody can have a chat with each other. So if you're interested, I recommend having a look there.
I think our time is up. Anne Youngblood, thank you so much for sharing with us some of the details of how you do your work and where you do it. And I know that you've just filed an application, expedition application to go back to
the Arctic.
The Arctic. I hope that works out.
Thank you.
Stay warm. Thanks all very much. I think there'll be more of these sessions next week.
Thank you.